All right, so this is where we left off. We talked a little bit about the name for, oh, I'm not connected anymore. Hang on. Get it when that happens. Oh, technology. Let's see something here. Oh, what? Oh, I know what's going on. There we go. There? Oh, there. Good. We talked a little bit how you name these substituents. So if you have it coming off like this, right? You notice, and the allelic, the allele substituent, there's an extra carbon here, so it's easy to miss that carbon. Vinyl is the double bond directly attached. So this is an example of a vinyl substituent, and we briefly named this. This is 1, 2, 3, 4, 5, 6. So it's 1, 5 hexadiene, and then on the 3 position we have an allyl group, so it would be 3 allyl 1, 5 hexadiene. Okay? What did I say? Oh, sorry, yeah, vinyl. I meant vinyl. Yeah, thanks. It's early. All right, so you guys remember cis and trans, right? So cyclopropene, cyclobutene, cyclopentene, cyclohexene. The parent can have a double bond in it. A ring can have a double bond in it. It can only be cis until you get to 8 carbons. And then once you get to 8 carbons, it could be cis or trans. So when you're talking about cis and trans in a ring, you really don't have to mention it until you get up to 8 carbons. And we can try drawing this. I always hate doing it. But we'll see how it goes. So, okay, first of all, start drawing if you're going to do it, draw a stop sign with a pencil because you're going to erase some stuff. And then the double bond has to involve this much of the molecule. That makes sense? Why that is? Because the double bond is going to have the 2 carbons that are double bonded, and then the carbons it's attached to. So those are the ones that you'll have to modify. Okay? So in a sense, you can think about it like if you're going to draw the double bond in. Oh, and you know really how important of a skill is this? Well, I just want you to get an idea how it's done. It's not, if you can't do it, it's not the biggest thing in the world. So that would be a double bond in an 8-membered ring. And then with your pencil, you just erase the 2 carbons that aren't trans. So then I would get like this. Oops, whoa, I selected way too much. Sorry. Oh, see. Like that. Okay. So that would still be 8. That would be a trans double bond in a ring. It's a little bit tricky to draw, but it's not a big deal. Now, here's something I want to point out to you, though. When we do, and you should read about Brett's rule. I'm not going to go over it. It doesn't get used that much. I will just tell you what Brett's rule says, essentially, is that when you have a bridged ring, you can't have a double bond. And the reason is the orbitals can't line up, so you could take a look at that. It's not a big deal. It's not used, I mean, as far as I'm concerned, it's not used very often at all. Okay, so for something like this, as simple as this molecule, what would you name this? It's going to be cis or trans. You guys remember what cis and trans mean? Trans. How do I know trans, though? Yeah, if you think about where they are, that little light pink line that I just drew here, right? This little pink line. One group's one way, one group's the other way from the line. That's trans. They're we say the lingo that we use. Can I use the word lingo?
You did.
I did, huh? Wow.
I think you're cool enough.
Lingo. Yeah, I don't know. Is that still a cool word? It is? Like your fancy lingo?
Yeah.
But you don't say AU in your fancy lingo.
Yeah.
Yeah, sorry. It's from a movie. Yeah, so I don't even remember the movie. I just thought it was funny when I heard it. Okay, so we say they're across from each other, or we say they're opposite of each other. They're not really like when you say opposite, you have to have a point of reference. They're opposite each other on the double bond. Okay, so or across from each other. That's the other term we use for this. These guys are across the double bond from each other. So these are all words that we use to indicate trans. But then the problem is you have molecules like the one that's shown on the bottom. Like you want to call this cis or trans, but like what would you decide to call cis and trans? It's just like, well, see this one's easy, right? Because there's hydrogens here and a hydrogen here. So what we do on this is we use easy notation. Have I mentioned easy notation to you guys yet? Oh, it's easy. So actually it is because you've done the hard part already. So if I draw a line across here, okay, and then think about where the largest groups are on the double bond. And by large, I'm meaning, remember the rules that we used for R and S? So what we do is we look for the highest priority groups based on the same RS nomenclature that we did before. So which is higher, hydrogen or nitrogen? So this is 1, all right? This is 2. Now on the other side of the double bond, over here, which is higher priority? Fluorine, so it's here and here. So then what you do is you look at the high priority groups and you make the determination, are they across from each other or are they next to each other? And in this case, what are they? The trans, or quote unquote trans, are across the double bond from each other. And so this is when we use the nomenclature for E and Z. E, everybody hates this. You ever find your stylus?
I didn't.
No?
I went through my car.
Wow. Well, if I show up with one, I bought it, okay? I'm just saying.
I wouldn't question it.
Entgegen. Oh, you have one. Oh, yeah, sure. Why not? Well, look at this one. You guys are all
No, this is mine. I'll take it.
fancy.
No. Oh, no, that looks like the one I lost.
Oh, yeah. You know, I had one just like this. Oh, that's pretty cool. I actually have a pen from Stockholm University that they have. They're just like they're cheapy pens that they hand out at the bookstore for like a
That's what
crow.
they are.
Yeah, they come with a soft end on it. And when I got it this summer, I'm like, what's the soft end for? And I'm like, oh, that's really cool. I finally figured out what it was like about a month ago. Yeah, this eraser is really weird. And then now I can't find it because now I know what it's for. I don't have any idea where it is. So. Yeah. Okay, so East is for Entgegen, and then of course everybody knows what that stands for. Zusammen is Z. Okay, that's the E and Z. Zusammen means anybody know?
I don't know.
Together. So that's a happy word. I'm Mr. Rogers of organic chemistry now, and zusammen is a happy word. It means together.
So Entgegen must be apart?
Entgegen means apart, yeah.
Alright, so then Entgegen would be the trans, right?
Yeah. But it applies to, so part, that spells apart down there. It implies more than just cis and trans because you can use it with compounds like this, where there isn't a cis or a trans, where you can't make that determination. Okay. Okay, so what is that one? Entgegen. So we say it's E, because I think that's a hard word to pronounce in English. Okay, so now, sorry, skip over this. This is all the rules I just talked about. So we're going to name some molecules now. Yeah. So, one on the left. You want to deal with the one on the left? What's the parent chain? First rule. Oh, come on, guys. It's too early for me, too. 7?
Yeah, 7.
Where are we counting from to? Top. That's 1, 2, 3, 4.
7 as a way.
Like this?
But you'd have to go right.
Oh, that's
4, 5, 6, 7.
never give you the most.
Why did I pick that one?
Um,
It's because I arbitrarily like it better.
the double bond is closer to the.
Yeah. So when I got to here, I looked to see, oh, that double bond's closer. What, right? So 2 double bonds, 1, 2, 3, 4, 5, 6, 7 this way, or 4, 5, 6. It's rather 6 versus 5. Okay?
So it would be 1, 5.
So it's going to be just the name, just like you do normal naming of stereoisomers. Name it first, and then figure out what the RSEZ is. Okay, so this is going to be 1,5-heptadiene, right? So 1,5-heptadiene, or hepta-1,5-diene, right? And then on 4, what do I have?
1, 2, 3 propene.
No, it's one of those special ones. It's allele, right?
Do you have to use names like that, or can you use?
Yeah. You could, yeah, let's just use those for the short ones. For the longer ones, then you can name the side chain and then put a YL at the end and call it a day. Okay, so now we have to do E and Z. What do we have to do E and Z of?
You're missing a substituent.
What's that?
You're missing a substituent.
I am?
The 3.
Oh, the 3-methyl. Darn it. I forgot about him. That goes in here. Why does he go there?
Because alcohol starts with an A.
Yeah, I'll start with an A. Is it 3? Yeah, 3-methyl. So for this guy right here. Right? No, just because it's alphabetical. Remember, the names and the substituents in the name are in alphabetical order.
Oh,
Yeah.
substituents first.
Yeah, and substituents come in first. Yeah. Okay, so
So, the E and the Z?
do I have? Yeah, let me ask you a question. Do I have to do E and Z for that guy? Whoa, that's just crazy. Do I have to do one for that EZ for that one?
No.
No. Why not?
There's 2 hydrogens on the other end.
Ah, I wanted to say it.
He said no. He said it. He said it first.
I'm sure
Yeah.
you did.
You said it more clearly, but
I
he
was
said.
going to say it too. Go ahead.
So what about this one? I know. You can say it all morning long. And all I'm going to say is, well, next semester it's at 1 o'clock, so that excuse will be gone. It'll be like, what's right after lunch? That's the one I hear at 1 o'clock. Then I'm like, don't eat. So what about that one there? Same thing, right? There's 2 hydrogens, so it can't be cis or trans. So this is the only one, right?
Yeah.
And it's easy to name that one because it's
It's cis.
Z.
It's cis, so it's Z. Okay, so you could, for this one, it'd be acceptable to say cis or Z. I will prefer, Z. Okay.
So where do you put the Z on that?
Oh, sorry, right here, the very beginning.
Now the allele, is that the U-type name?
Yeah.
Is it really?
Yeah, it's on. Hang on.
Not if I put protein, then.
Yes. You could, but if you said 2-propene, so there's a parent. Oh wait, that you could say ethene. But this is the 1, so that's 2,
Oh, okay.
right? So remember, wherever the parent chain attaches to a substituent attaches to the parent chain, that's the number 1 carbon. Okay, that's the rule in general. Although people don't always follow it, I'm just going to say that up front. That's the rule in general. So this could be 2-propenyl. And then the number in front of it, like this is the 5th carbon. See how much more complicated you're making this. 5, and then 2-propenyl, and then whatever the rest of them are. Yeah.
Maybe I'll just memorize the allele.
Yeah, you know, it's, yeah. Yeah, so it's not too bad. Okay, where was I? Oh, yeah. Okay, so before I get into this stuff, what I want to do is sort of give you a general overview of SN1 and SN2, or sorry, E1 and E2. So the reaction mechanisms for elimination reaction. So what I'm going to do is I'm going to draw up a generic reaction. Oop, I'm going to go back to a more darkly colored pen. Okay, so this is the E, just elimination in general. In elimination, you have an alkyl halide or something with a leaving group, okay? You have a base, and then what ends up happening in the reaction is you end up taking, there's a hydrogen here, you end up taking the hydrogen, and the bromine, and essentially removing the hydrogen and bromine, HBr, right, and forming a double bond. Now, just a couple of bits of terminology. The carbon where the functional group is attached, we call that the alpha carbon. So the carbon next to the alpha carbon is called beta. So I have a beta here. Do I have any other betas?
Yeah, one more.
Yeah, I got one more on the left-hand side. Okay. Turns out in elimination reactions, and I'm going to call this one beta 1 and this one beta 2. You know why I call it beta 1 and beta 2? Just because. There's no reason. Yeah. So, but I did it yesterday. I did it with beta 1 on the left and beta 2 on the right. People got really confused, and so I thought I would just make it. I don't know why. So primary versus secondary is not the reason I did that, but if it helps you, go ahead and do that, because it's going to be important here in just a second. Okay. So that's what I put up here is one of the possible products. Okay. Another possible product is to have this one. So if you can have a cis and a trans, then you will have a cis and a trans. Now we'll talk about stability in a little bit, but trans is going to be the more stable product. And see, just like it went back just now. I didn't do that. Still recording, I don't know. So the trans product is going to be more stable because there's less steric strain, right? The big groups are apart from each other. It's the more stable product, and so you end up getting trans as the major product of those two. On the other hand, there's a third product, and the third product looks like this. Okay? Now, it turns out for elimination reactions, like, you think about chemical reactions, there's three products. I already said one's going to be favored over the other, the cis versus the trans. But it turns out of the eliminations that come off of beta 2 versus beta 1, beta 2 is much more favorable. That is, of the products, these two are going to be my major products in most instances. I'll tell you later how you change that. And this will be my minor product. Now, real quickly, what do I mean when I say like major and minor?
The amount that you
Yeah, just the amount. So the major product's the one you have the most of. So on exams, when I ask for what's the major product of the reaction, then you would just give me the top two, okay, or the very top one, because there'll be more of that of the two. Or if I say give me the major and the minor products, you just have to draw all of them. Okay. So basically what you do when you do an elimination reaction, you look at where the leaving group is, and you look at where the beta hydrogens are, and between the leaving group and the beta hydrogens are all the possible positions for the double bond to be at after the elimination takes place. Okay? So we'll talk about E1 first, just very in brief. Now, E1 is a cousin to which mechanism do we know? We know SN1 and SN2. Guess what it's related to? SN1. What does SN1 mean? Not one step.
Yeah. It's 2 steps.
It's multiple steps, yeah. But what, do you guys remember SN1?
Yeah, it's 1 step.
So when you lose, what's the first step?
Oh, leaving group.
Loss of the leaving group, right? Same thing in E1. So an E1 mechanism the first thing that happens is this bond breaks. So in respect to SN1, same things that affect E1 affect SN1 and vice versa. So what you're going to end up with is a carbocation and the halide ion. Now, I'm going to draw this hydrogen in. I'm going to draw the mechanism for the major product. If I say draw the mechanism from the minor product, you draw the other hydrogen, okay? So, in the next step, what happens is the base, whatever the base is in the reaction, comes and grabs that hydrogen, right? And that forms a double bond. So you end up with that. So this is the elimination pathway for E1. Now, right, when you have a carbocation, there's a couple of things that you need to do all the time. You always look for rearrangement. And then for SN1, you look for the nucleophile and you attack with the nucleophile. And the nucleophile would end up attached here. And as it turns out, for E1 and SN1, they always compete with each other. So when you do a SN1 reaction and you're trying to get a product, right, almost always, but we almost never see it, almost always there's some elimination byproduct. Okay? So like when your percent yield is low, you're like, oh, my percent yield is low. I wonder why. That's one of the reasons why. Because there's another reaction that goes on and it's producing a product that you're not isolating usually. Okay? Okay, now, another note. This hydrogen, now, you guys remember I know we're not really focusing on pKa's very much, but do you guys remember the pKa's of alkanes?
Very hot.
Yeah, they're like super high, right? They're like 50 to 60. So there's not really many bases that can pull those off. So then the question is, what kind of crazy base pulls that off, right? And the answer is, it turns out just about any base can. The reason this carbocation over here is really unstable, right? Carbocations are not very stable, and as a result, just about any base can pull this off, because when that gets pulled off, the double bond forms and this carbocation goes away. Okay? The pKa, like estimates of the pKa, they're less than -2 for that hydrogen. So things like sulfuric acid, right? It competes with those kinds of things in terms of acid strength. It's a much stronger acid simply because the carbocation has become unstable and it really wants to get rid of that carbocation. So the pKa of this guy is less than -2, meaning it's a very strong acid and it's very easy to pull that thing off. So now let's look. Oh yeah, and then just remember, the kind of base that can do this can be weak. Okay? So let's look at E2. Hey, where have we heard, like, what's the cousin for this one, you think? SN2, right? So this, and SN2 happens in how many steps? One. This one happens in one step as well. Okay? So I'm going to get my alkyl halide. I'm going to draw the exact same alkyl halide. I have to remember which one I drew. Oh, and then put the hydrogen here. And then the base comes in. And that's going to break this bond. And that leaving group has to leave. Okay? So the product forms in one step. These are known as, and I didn't mention this when I talked about SN1, but these types of reactions where everything happens as one step are known as concerted reactions. Okay, so let's put a few more details on here. We're going to do the energy diagrams. So let's do E2 first. What's the E2 energy diagram look like? One hump. Now, I'm going to draw it like that. Right, reactants, products, one hump. Transition state. We'll talk about the transition state in a little bit. With transition states at the top. Now for E1, two hump. What if you have a bad leaving group? Guess what you have to do? You have to make it 3 humps because you got to make a good leaving group before you can get rid of the leaving group, right? Hey, and it's hump day.
Yeah, I know.
Oh, and it's mole day. So I hope you're all celebrating. It's 10:23, right? And I am such a chemistry nerd. My son Michael, who turned 11 today, is my mole day baby. So we did not plan that. It just kind of happened. And then when we told the doctor it was mole day, he was induced, right? The doctor's like, "Oh, that's a great idea." All right, whatever.
It's all for it.
So I'm going to have a hump, right, and another hump. Ooh, gosh, that's small.
I love that. Yeah, the camel. My daughter didn't get it.
Now, honestly, where this goes is not that important on this reaction, but a lot of times it's higher in energy in terms of like delta H. The product has a double bond in it. If you do the analysis of the bonds, you're breaking a sigma bond here, right? You're breaking a sigma bond here, and you're forming a pi bond and actually a sigma bond between the base and the H, okay? So 2 sigma bonds, to break those, takes more energy than you get back by forming a sigma and a pi. So in terms of energy, these reactions are usually endothermic, okay? Which means at low temperature, they favor being non-spontaneous, right? Because like if you remember,
Positive on this, right?
yeah. So delta G is equal to delta H minus T delta S. Let's say T delta S is not important. Let's say delta S is 0 or close to 0. Then everything is determined by delta H, right? So that means at low temperature, this reaction is non-spontaneous. Basically, you're forming, less stable bonds for more stable bonds, and that's always going to be non-spontaneous at low temperature. But if you look in terms of the reaction, here's one reactant and a base, right? How many products could you potentially have? 4 potential products, right? Even if it wasn't all of these, and we're just looking at major, it's this and this, but there really are at least 4 in this one, right? There's more products than there are reactants. So what do you know about, for those kinds of reactions, what do you know about delta S?
Oh, there's more spaces, so it's
Positive.
It's positive. So let's talk about favoring elimination reactions. If you have an elimination reaction, you want to favor an elimination reaction, what do you think you do?
remove bond.
Well, yeah, but in terms of just free energy, this, right? That's positive, and that's positive. So what temperature conditions is this reaction going to be? Yeah, increased temperature, right? T delta S.
Because that's going to have to be larger than the delta H, right?
Yeah, those are negative, right? So what you do is you increase temperature and it favors the reaction. It's also endothermic, so Le Chatelier's principle says endothermic reactions, you heat them up, it forces it to the product. The other thing to think about in these reactions is typically alkyl halides and alcohols that we produce them from have very high boiling points, and alkenes have very low boiling points. So as soon as the product forms in the reaction mixture, the product basically vaporizes out of the solution. Okay? Who hasn't done the lab yet? Who's doing lab today? No? You guys all did the lab, right? You haven't done the lab yet. Okay. So you guys remember when you were heating your solutions and you saw it looked like it was boiling? You didn't do the lab? Okay. So you guys remember when you heated your solutions, it looked like it was boiling, you saw the little bubbles, right? What was that?
Wasn't that the part of that gas that we're using?
Remember, we started with this. We started with this, right? And we ended with this. This boiling point was around 82, I think, 83. And this one's like 160-ish or 140-ish. 63. So think about what happens. You're heating this thing up. You only had the temperature to like 100 degrees, right? Yeah, so it was at 100 degrees. That's not boiling. This, when this got eliminated and you formed this, you're already above its boiling point. So it just literally, the bubbles you were seeing, that was your product that was being formed in the reaction as it was going. Okay? And that's why when they got the distillate out at the end, it was just full of product, which boiling point was only 82, 83 degrees. Okay? So that's one of the ways, I mean, for alkenes, the common way that we favor a reaction. For elimination reactions, we often favor elimination just by getting it hotter. Now, what does that mean? Right? 63 degrees, let's say the temperature, we heated it to 63 degrees, and we got substitution, and then we heated it to 100 degrees, and we got elimination. That's the kind of thing that I'm talking about. It's just hotter. But for some substitution reactions, you'll need higher temperatures. You'll need like 120 degrees, like we did the substitution reactions for the 1-butanol, right? You need much higher temperature. So if you want to get an elimination, guess what you have to do? You have to get even higher. So remember one of the things they talked about in the pre-lab for the substitution of the 1-butanol and 2-butanol?
Yeah.
Don't overheat it.
Yeah.
Right? Because when you overheat it, what happens? You end up forming a lot of alkenes, which then lowers your product yield. Okay? So these are all things that you have to think about when you're thinking about the competition between substitution and elimination. If you don't want elimination, just use the highest temperature you need to get the reaction started, and then don't go any higher than that. So on the test, I'm not going to ask you for specific temperatures. I'm just going to say, right, what conditions favor elimination? And you're going to say, it's hot. Hotter, higher temperature. Substitutions favored by lower temperature. What the temperature is depends on the reaction, okay? Okay, so rate laws.
We said certain pKa's also influence.
Yeah, and I'll get to that.
Okay, I was gonna
But
say, what's that that?
For this one, it doesn't matter as much. Because this activation energy is reasonably low for E1, reasonably low. The slow step is the formation of the carbocation. So the base, its characteristics are less important, right? But for E2, the characteristic of the base has to be it's a very good base. Strong nucleophile, strong base, okay? Which is why E2 competes with SN2, because if you have a strong nucleophile, then it tends to favor substitution. Okay?
So the only difference in the nucleophile and the base is the base takes a proton and the nucleophile just catches.
Yeah, the nucleophile catches that carbon, kicks off the leaving group.
Yeah.
It's the same thing.
It's the same thing.
So if you have like hydroxide, you could have both elimination and substitution, right? Right, so we'll get into that. Okay, so rate laws. For E1, rate equals K times what?
The concentration of the leaving group?
Not the leaving group. Look at this. This is the rate determining step. So it's just going to be the concentration of your alkyl halide. Okay.
The substrate?
Substrate. I'll just do this Rx. And it could be an alcohol too. But then in that case you have to convert it over. So that looks just like an SN1 rate law, right? And for E2, what is it going to be?
Concentration of the substrate and concentration of the
Yep. K times Rx and base. And the base is really just another name for the nucleophile. Okay? But it turns out there's non-nucleophilic bases, and we'll talk about those. Okay? Like pyridine is a non-nucleophilic base. It can't get in because the base is too sterically hindered. Okay? Can't form those bonds easily. Oh, my arm's getting tired. All right. So before we go on into E2 reactions and talk about those in detail, we're going to talk a little bit about alkene stability. So what I've got up here is I've got the combustion reactions for cis and trans 2-butene. So combustion is, right, whatever you're burning, plus oxygen produces heat, right? That's definition of combustion. Uses oxygen, produces heat. The combustion of a hydrocarbon always uses oxygen and then produces the oxides, carbon dioxide and water. Okay? So if you do trans 2-butene, right, negative 2682 kilojoules per mole. If you do cis 2-butene, negative 2686 kilojoules per mole. Now, which one releases more energy? Cis, right? Because it's a negative number and it's larger, so that means more energy is released. So this reaction, the combustion of the cis, is more exothermic than the trans. So what does that mean about cis versus trans in terms of stability?
Lower energy.
The one that gives you less energy out was more stable to start with. Okay? One way of putting it up is to put it graphically like this. I have the cis alkene up on the left, the trans alkene on the right. This one releases 2682 kilojoules to form 4 CO2s and 4 waters. This one releases 2686 kilojoules to form the same product. So since they're going to the same product, you can tell in this case that the trans alkene, right, is more stable than the cis alkene. They do the same analysis with substituted alkenes, and this is what they find. This double bond has one substituent on it, okay? One alkyl substituent. Oh, hang on. This double bond has 2. This double bond has 3. And this double bond has 4 substituents. So we talk about the degree of substitution of the double bond. All right, this has 4 degrees of substitution. This has 1 degree of substitution. 4 degrees of substitution is more stable. Okay, where have you heard that kind of like terminology? Like more substituents, it's more stable. Carbocation stability, right? It's the same trend as carbocation stability. Double bonds are made more stable by the substituents. Now, okay, let's back up for a second then. When carbocations are made more stable, why do carbocations get more stable when they have more substituents on it? Induction, or what's the big fancy word? Oh, you should know this word. Hyper. Yeah. Why should you know it? Because you're kind of like always moving, but that's okay.
Not this morning.
Yeah, I know. So we have induction or hyperconjugation. So carbocations. I got disconnected. This is our lovely network. Oh, you know why? Yes, it's carbocation stability, right? So substrate has an effect on whether or not you have the possibility of E2 or E1, just like you do SN1 and SN2. You can't form a primary carbocation, so as a result, you have on primary alkyl halides, you only have SN2 and you only have E2, but those two will compete against each other. Okay? Now, in SN2, what do we know about tertiary carbons? Yeah, it can't happen. Why? There's too much steric hindrance. Nucleophile can't come in. Okay? So let's say you take a look at this situation where you have a nucleophile / base. Hydroxide could be either. Okay? It tries to do an SN2 reaction. It can't get in there and attack and push the leaving group off. But look what happens in elimination. In an elimination reaction, right? it doesn't have to get to this carbon. It's like a long range, remember I talked about it's like a long range SN2. It could take a hydrogen that's away from the leaving group on the beta carbon and cause the reaction to happen. Okay? So this reaction is not as bothered by steric hindrance of the substrate as this reaction is. In fact, the order of reactivity is that tertiary alkyl halides react faster by E2 than primary. Okay? So tertiary is faster for E2 than primary. So the order of reactivity for SN2 and E2 are the opposite. Okay?
But E2 will react with both primary and tertiary,
Yes.
or SN2 won't?
It's the opposite in the sense that tertiary, hang on, let's do it like this,
Higher rate.
is faster. Whereas for SN2, tertiary is the slowest. Okay? Okay. So as it turns out, the reason for this is that has to do with the nature of the transition state for this reaction. So in order to sort of understand the transition state, we'll take a quick look at the energy diagram for the reaction. But this trend, right, primary, secondary, tertiary, is essentially the opposite of what you see at SN2. It's much faster at a tertiary than it is at primary. So what does that mean about the transition state if it's faster?
Less stable.
Transition state, right? Think about like your energy diagram. There's one on the next page, but I'm going to just generically. Right? This is your transition state. There's reactants. Here's products.
Oh, so it's gonna look more like a reactant?
It looks like reactants, but what is it? What do I when I say okay at tertiary it's faster? Let's say this is primary, right? And I say at tertiary it's faster. What does it mean?
Lower activation?
Lower activation energy. Okay. And as it turns out, degree of substitution is important. More substituted is faster. What is that sounding like?
More hydrogens.
More hydrogens? No, it's not the more hydrogens. That's actually a good argument, but it turns out they've studied that and it's not true. Sorry. What if the transition state is getting lower in energy, right? By increasing the degree of substitution, right? What does that sound like may be happening? That for the, yeah, it sounds like it's kind of like SN1. Has to do with stability of the carbocation. But we don't have a carbocation in this mechanism. They don't form. Okay? Okay, so as the leaving group leaves, okay, if this leaving group is a good leaving group and wants to leave the structure, then it ends up that at this carbon, the carbon begins to appear positively charged. If it's a good leaving group, right, it's far away from the nucleus. That nucleus appears to be positively charged, and as a result, the leaving group can leave easier as a result of more degrees of substitution. Right? More degrees of substitution means it's easier for the leaving group to take those electrons and run away, because the substituents are now providing electron density for that nucleus. So that substitution at this carbon allows this energy to be lower and allows for the reaction to go faster. Okay. So in essence, with the primary in an E2 mechanism, with the primary substrate versus a tertiary substrate, what you end up doing is you end up lowering the activation energy because it's easier for the leaving group to take off. Okay? Okay. So we say, there's this term that we use, regioselective or regioselectivity. If you can have multiple reactions or multiple products formed out of a reaction, and one of them is favored, we say that's regioselective. That if it's one part, think about what is a region? Region's an area, right? If one area of the molecule preferentially reacts versus another, we would say the reaction is regioselective. And this gives us products, distributions where one product will be more favored than another. So let me draw this on the board for you. Okay, so E2 mechanism, regioselective. Identify my alpha carbon.
It's one with the leading group.
It's the one with the leaving group. So this is alpha. Okay, where are my beta carbons? Just to either side, right? So beta here. So that beta 2, and I'm going to call this beta 1. I just reversed the molecule from before. I'm just kind of running you through the thing. And there's a hydrogen. So now, in this particular reaction, I have two possible products. The two possible products are here for the elimination or here for the elimination. So when I do the elimination, if it's beta 2, then I end up getting this. And if it's beta 1, then this beta hydrogen leaves, and then I end up with this. So which one of those is more stable? Top one.
Top one.
Two substituents on the double bond, one substituent. So think about the energy diagram for an E2 mechanism. It looks like this, right? But we know that this double bond is more stable. So let's say this is the energy for that as the product, and the energy for this is the product goes like this. Because it's going to be lower. So the way they think about this is, since that's lower, it actually pulls the transition state energy down.
Slightly lower.
Yeah, so slightly lower activation energy allows it to be the major product. It forms faster, and it is also the more stable product. So it's both the kinetic and thermodynamic product. So when you do an E2 elimination, you typically get the more highly substituted double bond versus the less highly substituted double bond. This is known as the Zaitsev elimination. And your book, which makes me partially crazy, likes to use the term Hoffman product for the less stable. Now, one F, sorry, and two N's. I don't use that. I use anti-Zaitsev. And I suppose there's reasons why people don't use anti-Zaitsev, but they're in the small percentage. Look up Hoffman elimination, you'll find all kinds of reactions on amines. Amines turn out to give you a lot of Hoffman elimination products. Okay? Typically, though, people will just call it Zaitsev and anti-Zaitsev. Zaitsev means most stable. Zaitsev's a guy's name. Doesn't actually mean most stable. But in terms of what we use it as, you have Zaitsev as the most stable, and then you have the anti-Zaitsev. Since Zaitsev is the most stable, the anti-Zaitsev must be the least stable.
So the Zaitsev is the major product.
Zaitsev is the major product when you have a good leaving group. Okay? And so far, all we've talked about is good leaving groups. Okay, so here's some funny data. Just want to show you this really quick, and then we'll talk about it on Monday. I will be lecturing on stuff on Monday that you'll be tested on Wednesday, so get caught up. Okay. Zaitsev, most stable product is the major product when you have that base, and the minor product when you have that as a base. Okay. The bottom base is big and bulky. Right? So we'll talk about steric hindrance is a problem in elimination reactants, or it's a curse or a blessing depending on what you want to call it. You can get anti-Zaitsev, you can get the less stable product by changing the base. Okay? So that's actually a good thing. So let's wrap it up.
All right. Good times.
Dr. King, did you ever add our